chemist, having obtained his PhD under Professor Guy Lloyd-Jones, and then carried out postdoc in mechanistic studies with Professor Donna Blackman at Scripps. And David came back to the UK in 2011 to join Syngenta's process studies group as a process chemist, and has been specialising ever since in applying physical organic chemistry in the support of process development and manufacture. So over to you, Dave.
Thanks very much, Catherine. Yeah, and to hear guys in the audience as well adds a bit of extra pressure, brings back some memories as well. So let me just share my screen. Okay, so today I'll give a bit of a specific talk on an example, really to try and highlight how the timelines for fundamental understanding are really required to enable earlier decision making. I think Nessa alluded to this earlier, and this is for process development. But hopefully I can show that this can be enabled in some circumstances through PAT-enabled experimental design and also simulation. And the growth of that area, coupled with some of the topics that Nessa talked about earlier, I think really do give potential to accelerate understanding of some quite complex systems. So in terms of just an overview of Syngenta, there are two main streams to the business. One is crop protection, which is looking for new active ingredients, and the other one is seeds. I work in the crop protection division. And this is a typical herbicide. This is pinoxidin, which is an ACCase inhibitor. Typically, it's invented using similar kind of approaches in the pharmaceutical industry. And this is the kind of molecular structure and complexity that we look for in the compounds. So to move on to the case study that I'll talk about today, we had a new ACCase inhibitor in development. So this was back in around 2012. As mentioned earlier, we had about 18 months to pilot, and our pilots are typically looking towards about half a ton to a ton scale of material. So they need to be reasonably well developed. And we'll often get the roots from process research with pretty significant information in terms of selectivity and how it behaves, but may require optimization. We have about 18 months to do so. And this particular example, we wanted to understand how better, or to deconvolute, we had two technology options to form this key intermediate termed TMF for incorporation into the target molecule. And we wanted to understand what the best approach was. So the first, we had a decision. One was acid catalyzed and one was gold catalyzed. In terms of the acid catalyzed route, we definitely worked to try and understand what's the optimal here. We did a series of kinetic studies to understand how it behaves and the mechanism behind them and understand the selectivity patterns. So first you got an acid catalyzed Meyer-Schuster rearrangement to form these intermediates, HYE in the formulated version. But you also got two undesired pathways as well. One to form this diketone, which was particularly problematic because it's difficult to remove. And problematic for later stages, and therefore for AI quality. And then you had this polymerization, which just lowers yield, but could be managed. These two interconvert very cleanly to the final product, TMF. So the challenges really were the throughput was not great, and really how to deal with this diketone was a real problem for us. So further work was done to look at this gold catalyzed rearrangement using this gold carbene complex. And the advantage of this route was that it was very high yielding, around 98%, very high selectivity, and crucially no diketone, which made a lot of the work up a lot simpler. And it had a reasonable cycle time at the loadings that were evaluated. But obviously using gold, it's not cheap. And so we had a target loading of 0.01 mol% for economic viability. And then also we had to, it was noted that some reactions just didn't initiate, and some sort of initiated, but they didn't get to completion, particularly around the target loadings. So we really asked a question by the teams, by the process development teams, what's going on with the catalyst stability here? So in terms of the approach that we wanted to use when thinking of catalyst stability, a very common approach is to use Blackman's RPKA, or reaction progress kinetic analysis. Typically, this is done using colorimetric analysis. It can give you rate information directly, which is very valuable. But actually, you can utilize integral data, such as concentration data, such as IR or other sources, and then use the time shift analysis to compare the rates of a reaction you started here with one that started with the rate of a reaction which has gone through part of its cycle already. I'll come back to that in a bit more detail. The advantage of IR, especially in this case, is we actually had two sequential steps and they overlapped, as you can see from the profile. So actually a heat flow would have been far too confusing to deconvolute calorimetrically. And so an IR did give us the signals that we could work with for each independent species. So the typical approach would be, well, let's try running a few different catalyst loadings and look at the rate behavior. Typically, we would expect a first order dependence upon the catalyst. So we ran three concentrations, one around the target loading. So we were pleased to see that the reaction did kick off, which is encouraging. And we were concentrating at this stage just on this first step. So we ran the time course normalization approach. So the theory of this is if you multiply the time course by the catalyst loading raised to a certain power, you can deconvolute the power of the order of the reaction in the catalyst. And I mean, this can be thought of quite easily by thinking, well, if I double my catalyst, I double the rate, I halve the time to completion. So if I multiply the time axis artificially, it should overlap. What was quite confusing is that at higher catalyst loadings, we got the expected order of 1, which thinking about the chemistry and what we know of catalysis, that's quite typical. But actually, when we noticed at lower catalyst loadings, as kind of target loading, that we got a greater than first order dependency in catalyst. And so this was quite confusing at the time. So what this told us really is we needed to look a little deeper. But we didn't actually need to do any more experiments. We could then just reprocess the data by doing some initial rate analysis. They were typically quite zero order in the first phase, making this semi-applicable. And what we could see is that the intercept doesn't go through the origin. It actually goes through at a positive position on the x-axis, suggesting that there's a certain amount of an inhibitor, which is inhibiting the catalyst. This was actually attributed back to the substrate HDO. But now knowing that there's an inhibitor that's killing part of the catalyst, we wanted now to understand, well, actually, how fast is that occurring? Indications from the kinetics, I mean, from visual analysis suggests it could be pretty fast relative to turnover. But the way we did this was take advantage of the PAT technologies, and we did a catalyst dosing experiment where we dosed the catalyst in aliquots, and you can see for the first two, there was very little reaction. And then the reaction started to accelerate once we got over the threshold, which corresponded to the impurity level previously calibrated. And then by increasing, we could actually calibrate first order dependence as we'd expect. So this really did confirm that it's an inhibitor that acts very, very quickly relative to catalytic turnover. So when we now took account of that, so if we take the total catalyst concentration and remove the amount that we know from the inhibitor, and then to give us an amount of active catalyst that we're putting into the system, we can then reperform the time normalization and we get overlay. So this confirms that that did account for that difference and that discrepancy in the orders, and we've got a decent first order overlay. But we can actually take that one step further. So now we know the level of the impurity in what was the distilled stock of substrate. We could actually run reactions with the same amount of total catalyst for different qualities or different pre-treatments, so crude from the supplier or just pre-filtering a solution of the substrate, and run the kinetics. Then do an incremental adjustment to try and achieve overlay by adjusting the amount of impurity, which then gives us, or adjusting the level of active catalyst, which then gives us the level of the impurity. So what it gives us is a very fast way to understand the level of the impurity in this case, and which pre-treatment will be viable to achieve the target loading. So we can see that actually we could have a filtered solution, or we could actually distill the substrate prior to the reaction. What we could also do is then correlate the analysis of these samples with some offline analytics. And I mean, the impurity was nothing exotic. It was really just chlorides in the substrate, or halides, sorry, in the substrate, predominantly chloride. and that will obviously bind to the gold and inhibit turnover. So that then allowed us, you could think of maybe setting specifications with suppliers to manage it in production. So we've understood why some reactions don't start, because that's linked to the substrate quality. But why do some start and then not reach completion? Well, this is when we started to use the reaction progress kinetic analysis approach. And as we'll see in a minute, we had to modify it slightly to account for the changing in the amount of active catalyst, because we'll ultimately change the amount of substrate that we put in. So the way the RPKA approach works is you run an initial reaction that we'll call our standard reaction. And then we consider what the substrate concentrations are likely to be at a percent conversion, in this case 50%. And the difference between the two reactions is now one's done 2,000 turnovers and you've got some of your products present. Just to note here that water in this case is catalytic by definition, so it doesn't change. So what you then do is you run a reaction under the start a reaction under these conditions, but obviously this will have the same substrate concentrations, but it won't have done the same number of turnovers and doesn't have product in it. And then by doing the time shift analysis, you can compare the rates to determine whether it's stable. The one slight change we had to make is change the amount of added catalyst that we put into the system, because we have a different amount of the impurity that we're adding to this reaction compared to the other one. By doing that, we can see that we've actually got quite a stable catalyst. If we hadn't done so, that would appear as an on-cycle deactivation. So we would have made the conclusion, well, actually our catalyst is inherently unstable, where it's not during this time frame. To check it, we ran two more tests, one at 25% conversion and another one at 75% conversion, all giving decent overlay. So it suggests our catalyst is stable over this time frame. And we've done that now within 7 experiments, catalyst order, and then the stability analysis. What we can also do is take it a little further, is actually because the water is not changing in the reaction, it's constant, then we can actually look at the reaction order in substrate concentration. We can see actually at the high concentrations, it's almost zero order. And what we're able to do is use NMR-XC analysis of the binding coefficients by analyzing the catalyst at -35 to 5 degrees. And then we used a Van 't Hoff plot to extrapolate that to 140 degrees where we're running chemistry. So obviously that's quite a large extrapolation, but that will give you this binding constant. What it did do though is give us a forward and reverse rate constant, and using our Arrhenius relationship. So by fixing the reverse rate constant, we could then actually simulate what that binding constant would be, and they're not too far outside of agreement. The important part of this is now it gives us an idea, and this will be important coming back later, how our catalyst speciation changes during the process. And then this can give us ideas in terms of how we want to operate it, and whether there's any regimes where it may not be stable. Okay, so it looks as if the catalyst is stable in the first step, but at this point we don't really understand. We haven't really looked at the second step of the reaction, and typically this is a slower step. And our process development colleagues said that actually they tended to fail during this phase of the reaction. So we wanted to take a look. So what we did was isolate the intermediate and start doing an independent study on this particular step of the reaction. So in direct analogy to what we ran before, we ran two reactions. A slightly higher catalyst loading just to help us with the cycle time. And we ran them at 2 different catalyst concentrations, and then we performed the overlay analysis and found that this first order in catalyst and the minimal impurity decomposition at this particular concentration. We were a bit less interested in the impurity mediated decomposition in this particular case because the substrate had been pre-purified and we won't be sourcing it directly. It will be made as an intermediate. So what we then did was run the RPKA analysis, and in this case it was a little simplified because we could just use the total amount of catalyst put into the system. And by performing the same excess experiment, what we did see is a slightly faster rate for the same excess experiment. Now this suggests that the presence of the product or the number of turnovers that you've done in the first reaction has slowed the catalysis effort, so taking the catalyst off cycle or deactivated it. And we did repeat this as it's quite a subtle change, and it did seem to be really useful in terms of that difference. So the way to deconvolute between product inhibition and catalyst deactivation is to run the same excess experiment again, but this time add product in, and then it depends on which curve it overlays with. So what we can see is it overlays with the original curve. And so what this says is that actually that first 1,000 turnover numbers doesn't have a massive impact on catalyst stability. But there is a small product inhibition by the TMF final product, but it's relatively weak. What was confusing is, well, actually what we're saying here is our catalyst is inherently stable, which is in contrast to what our process development colleagues are observing. So what we thought is actually, is it something to do about the catalyst distribution in this phase of the reaction? So we performed a multiple addition experiment where, to the same excess experiment, we waited 300 minutes and added the same amount of substrate again. Now, obviously, there will be some level of product inhibition, but what we saw is a significantly slower rate of reaction. So what this is suggesting, that holding the catalyst in that end of reaction distribution, or at least in this phase of the experiment, it seems to be less stable. What we also know from our binding studies is that actually at higher temperatures, the binding is going to be less favored. So we're likely to have more free catalysts, and also you're likely to accelerate deactivation pathways at higher temperatures relative to the desired pathway. And so for those reasons, we were running most of our studies at 140 degrees, where the process is run at 160. And also you have slower operations due to scale. And so it is likely that that actually in this phase of the reaction, the catalyst is less stable when it's in its unbound state, and this could account for why we were getting incomplete reactions. And what we could do is, as we run all these three experiments, we get a kinetic simulation to give people an idea of that catalyst distribution and how it evolves through the process. And so what we can see is initially a reasonable proportion is bound to the HYE, and then over time you get an increasing amount of the TMF bound complex and the unbound complex. What we weren't able to do is define which one was less stable. You could do that through several designed experiments, but the project finished by that point. But what we could identify is you could enhance by lowering the temperatures, but you will obviously then get a cycle time penalty. So we want to reduce catalyst loading, which will slow rates, but if we want to reduce temperature as well, we'll also slow the cycle time as well. So for instance, if we're already at 8-hour cycle time, and we reduce our temperature by 20 degrees, that's likely to lead to a cycle time of 30 odd hours, which is really too long. But actually thinking back to what we understand now and what we think back to the two processes, the final recommendation was to run the first phase of the reaction using the gold catalyzed process, because we know it's A, very selective, B, it's quite quick, C, we can now manage the impurity level in the substrate, and therefore we can optimize catalyst loading to the desired target without challenges of deactivation, as we can run it at lower temperatures and maintain cycle time, but then run it as an acid catalyzed rearrangement afterwards, as we know that that process is highly selective. So having achieved this, just to give an indication of scale, for a 500-ton building block, which would have been the kind of scale for this active ingredient per year, that would be 69 kilos of gold, which seems a lot in isolation, but actually that's only 4 parts per million of yearly gold production. So in reality, what we've done is optimize that pretty significantly, but you can see how that would then scale up if we didn't optimize those loadings. So hopefully I've given a quick overview how PAT-enabled experiment designs can provide rapid information or fundamental understanding of to aid process development. Really, it's enabled by application of PAT techniques, experimental design and simulation. And this whole study was 21 experiments in about 6 weeks. What we were able to give is an overview of reaction driving forces for selectivity, rate, and yield in that time frame, and enabled evaluation of novel process concept. And that information really did guide the development of the product. However, there were certain complexities with the system, but actually it's a relatively simple system from a selectivity perspective. And so I think what's quite exciting is you've seen some of the talk from Nessa earlier, and you can see how the positioning in terms of your data landscape will evolve. And as you can see, technological and data management improvements, it'll be interesting to see how we can accelerate understanding of more complex systems. So for instance, ones where you may have phase transfers, you might have selectivity challenges that could become complex, and actually how that multi-dimensional data and information space can complement accelerated understanding of those systems. So I think whilst this gives you a nice indication of what can be achieved in a short time frame, hopefully it can be applied in future more complex systems. So with that final thought, I'll just wrap up and just acknowledge the team from across the globe that worked on this particular project, teams in process development, analytical, and crop protection research in the UK. So thank you very much.
Brilliant. Thank you very much, David, for an excellent talk.